Hi everyone, welcome to the next lecture video. Today's topic is series resonance. Okay, so this is a very important topic not only in GATE but in commonly asked in various technical competitive exams. Okay, so listen carefully, watch this video till the end. Okay, don't skip any portions of this video. So watch this video till the end. We can go directly to the concept.
If you haven't subscribed to this channel yet, subscribe to Easy Abhay Tricks and don't forget to click the bell icon for immediate updates.
Now, what is resonance? Okay, so resonance occurs only in RLC circuits only. RLC circuits only, right? So consider this circuit. It has resistance, inductance and capacitance connected in series, right? And connected to an alternating voltage supply, right? So the resonance occurs in such type of series RLC circuit is called as series resonance. What is a resonance? First of all, the circuit is said to be in resonance if the current is in phase with the applied voltage. So when the current is in phase with the applied voltage, only when the circuit is resistive in nature, only in a resistor. If the circuit is resistive, our current is in phase with the applied voltage. You remember, if the circuit is inductive, then the current lags, right? And if the circuit is capacitive, then our current leads the voltage. You remember? Right? So in the resonant case, the circuit is said to be resonant if the current is in phase with the applied voltage. It means that the circuit is resistive. Now what about this inductance and capacitance then in a series RLC circuit? Then the inductance and capacitance, that is the inductive reactance and the capacitive reactance gets cancelled each other, right? So if it is cancelled each other, then the resulting resistance will be only due to the resistor alone, so that the current is in phase with the voltage. So that condition is called as resonance. Understand? So the circuit is said to be in resonance if the current is in phase with the applied voltage. So it means that our inductive reactance will be equal to the capacitive reactance. Understand? So the resulting impedance will be only resistance. So this condition is called as resonance condition. Okay. Now another definition is that resonance is the phenomenon in which where the output of the circuit is maximum at one particular frequency. That condition is called as resonance. That is our output, that is our current. Due to the generation of our input voltage, the output current is generated, right? So the resonance is a phenomenon in which the current, that is the output current, is maximum at a particular frequency. So that particular condition is called as resonance, and that particular frequency is called as resonant frequency FR. Understand? That is the frequency at which resonance occurs is called as the resonant frequency, right? Okay, this is all about resonance in common. You understand? So resonance is a phenomenon in which the output is maximum, that is the current is maximum at one particular frequency, right? So usually either we will keep the value of frequency, the resonant frequency, that particular frequency of the alternating supply to be constant, and we will vary the XL and XC and make the circuit to be resonant, right? Or we will keep the XL and XC and constant, and we will vary the frequency of the alternating supply to be resonant, right? So either we can vary either the frequency or the reactances. Understand? So this is the concept of resonance. Okay. So at resonance, what is the condition? The inductive reactance will be equal to the capacitive reactance. Correct? So in this case, the resulting impedance will be equal to resistance alone. That is the resulting circuit. That is a resonant circuit will be resistive circuit, right? Not a reactive circuit. The reactance gets cancelled each other. What is the reactance? Inductive reactance, capacitive reactance. That is XL will be equal to XC. So both gets cancelled each other, and the resulting circuit will be only resistive of nature. So that condition is called as resonance, right? That is normally in a series RLC circuit, what is the value of impedance? We have seen this equation, right, in our previous videos. So Z equal to R plus J into omega L minus omega C. That is Z equal to R plus XL minus XC. You remember? So in resonant condition, the inductance will be equal to the capacitance, right? So both gets cancelled each other. Reactive inductance will be equal to reactive capacitance, right? So both gets cancelled each other, and the resulting impedance will be equal to R. That's how this condition gets appeared, right? So this is the value of Z. So in case of resonance, both the reactive inductance and reactive capacitance gets cancelled each other, right? So both are equal, so they gets cancelled each other. So the resulting impedance will always be minimum. Keep this point in mind, very important point. That is, in a series resonance circuit, both gets cancelled each other and the resulting impedance will be minimum, will be a low value that will be equal to R. Keep resonance circuit. What about the resulting current? The current will be of maximum or minimum. The impedance is minimum in a series resonance circuit. So the current will be obviously maximum according to Ohm's law, you remember, right? So there will be a maximum flow of current. So that current will be equal to V by Z. What about Z in a series resonance circuit? Z will be minimum. That value will be equal to R, right? So I max equal to V by Z minimum. That is I max equal to V by, what is the value of the minimum impedance? It will be resistive. That is V by R. Understand? So it is all about maximum current in a series resonance circuit, right? Now coming to the frequency. Right. So at resonance, what about resonance? At resonance, the value of inductive reactance will be equal to capacitor reactance. That is XL equal to XC, right? What is the value of XL? Omega L equal to XC is 1 by omega C, right? So on cross multiplying, omega square equal to 1 by LC, omega equal to 1 by root LC. What is the value of omega? Omega equal to 2 pi f, right? So on substituting this value, f equal to 1 by 2 pi root LC. So this frequency is called as resonant frequency. Either you can write it in the form of omega r or fr, right? So it's a commonly used formula, right? So many of the technical competitive exam prefer this question, right? So this formula is very, very important, right? This is the resonant frequency. Resonant frequency FR. So what is the resonant frequency? Resonant frequency is one in which resonance occurs. That is, in other term, we can say that at resonant frequency, impedance is minimum, current is maximum. Also, you can say that at resonant frequency, the reactive inductance will be equal to reactive capacitance. Also, you can say that at resonant frequency, the impedance will be equal to the resistance alone. Understand? So this is all about series resonance. Okay. Now we can see the behavior of a resonance circuit below the resonant frequency and above the resonant frequency. Okay. So consider this plot. This plot shows the this graph is a plot between the frequency and the output current, right? Frequency and the output, right? So the current varies with respect to frequency, right? Initially it starts from 0 and increases to a maximum value of current and then goes back to 0, right? So the frequency at which the current value is maximum is called as resonant frequency. This is called as FR or omega R, resonant frequency, correct? So this graph is called as our resonant curve. This graph is called as resonant curve. The plot between the frequency and the current, or the frequency and the output, right? Okay. The resonant frequency is a frequency at which the output is maximum. Understand? Now coming to the behavior of circuit, right? Now below the resonant frequency, right? Below the resonant frequency there are several lower frequencies, right? So below the reference frequency, consider a frequency f, right? So if f is less than this resonant frequency, what about the behavior of the circuit? Okay, so listen carefully. This concept is very important, right? So below the resonant frequency, that is at low frequencies, right? What about our inductive reactance? What is XL? XL equal to omega L, correct? And what is XC? XC equal to 1 by omega C, correct? So at low frequencies, what about XL? XL will be low, right? And what about XC? XC will be higher, right? So if omega is lower, then obviously XC will be higher. In short, we can say that XC is greater than XL. Right, that is the circuit is predominantly capacitive. Understand? That is at low frequencies below the resonant frequency, the circuit is predominantly capacitive, right? So in a capacitive circuit, the current leads voltage, right? The current leads voltage by 90 degree. That is phase angle is 90 degree, right? So this is called as, if the current leads voltage, then that power factor is called as leading power factor. You remember, right? So at the frequencies less than resonant frequency, the circuit is predominantly capacitive. This is what you need to know. Understand? Predominantly capacitive. Okay. Now Coming to frequencies greater than resonant frequency. So at frequencies greater than resonant frequency, that is at higher frequencies, that is at higher frequencies. What about XL? XL equal to omega L, correct? And XC equal to 1 by omega C. So at higher frequencies, obviously XL value will be higher. And at higher frequencies, XC value will be obviously lower, right? So at frequencies higher than resonant frequency, the value of XL will be greater than XC, obviously, right? Understand? So the circuit will be predominantly inductive when the frequencies are greater than the resonant frequency. Understand? Now, if in an inductive circuit, the circuit is inductive, then what about current? Current lags behind the voltage by phase angle of 90 degree. Understand? So the circuit is called as the circuit has a lagging power factor. You remember? What is a lagging? What is a leading? You remember, right? In the previous lecture video, we have dealt the concept of power factor, right? Next, the final concept, that is our resonant frequency concept. So at resonant frequency, if the frequency is at resonant condition, then what about the value of XL? XL will be equal to XC, correct? And the impedance value will be equal to R, right? So what about the circuit's behavior? The circuit's behavior will obviously resistive. The circuit is predominantly resistive. So in a resistive circuit, what about the phase angle? The voltage is in phase with the current, right? That is the theta value will be 0 degree. Phase angle will be 0 degree. So what about the power factor in this case? You remember? The power factor will be 1. That is cos theta. Cos theta is a power factor. Cos 0 value will be equal to 1. So the power factor value will be 1. This is a very important concept. So this is the resonant curve. So at resonant frequency, the circuit behaves as a resistor. The circuit behaves as a resistor. And below the resonant frequency, the circuit behaves as a capacitor. And greater than the resonant frequency, the circuit behaves as an inductor. Keep this point in mind. Okay. So consider a series RLC circuit, that is RLC, right? So in a series RLC circuit, the entire energy supplied by the source is either stored in the inductance and capacitance, right, in one half cycle, and then returned back to the source in the other half cycle, right? So in turn, in result, there will be a generation of oscillations, right? So to reduce the oscillation, the value of resistance is used in a resonance circuit. Understand? So that condition results in resonance. Obviously, you know what is resonance, right? So due to the generation of oscillation due to this inductance and capacitance, okay, there will be a addition of resistance in our circuit, right? So this resistance controls the oscillations produced by this reactance. Understand? So this value of resistance must be higher. This value of resistance must be higher to reduce the oscillation, right? This point is very important. Keep this point in mind. So the value of this resistance will be higher to produce low oscillation. Understand? So consider these three resonant curves. Okay. So the three resonant curves varies with different resistance value, that is R1, R2 and R3, and this R3 value is greater than R2 greater than R1. Okay. That is, the R3 value was higher comparing to the other two resistances, right? And the curve, see the curve, that is, the greater the resistance value, wider the resonant curve, right? So this R3 value was greater, so that resonant curve is very wider, right? If the curve is very wider, the bandwidth is also very larger. That is, B3 bandwidth is the bandwidth of the corresponding resonant curve of this resistance R3, right? That bandwidth is larger. If the bandwidth is larger, that selectivity is poor. Understand? So the resistance, if the resistance is larger, the resistance is directly proportional to width of the resonant curve, correct? So if the resistance is larger, width of the resonant curve is also larger. So if the width is larger, obviously the bandwidth is also higher, correct? So if the bandwidth is higher, obviously the selectivity is very poor. The selectivity is low. This is our condition, right? Okay, got it? Okay, got it. So if the resistance is larger, width of the resonant curve is larger, and if the width is larger, obviously the bandwidth is higher, and if the bandwidth is higher, the selectivity is very poor. Okay, and in the wider curve, this is the R3 curve, is the wider resonant curve, right? The current value is particular on current, right? There is one lower current. And coming to this other resonant curve R2, this R2 is slightly lower than this R3, correct? And due to this lower value of R2, it has a somewhat higher current, correct? I2, this is I1, this is I2, right? And coming to the bigger curve, that is the narrower curve resulting due to this R1, right? This R1 resistance is very lower comparing to this R2 and R3. So due to this R1 curve, the current value is I3, that is the I3 value is maximum. So we can also say that if resistance increases, the current decreases. So obvious rule due to the Ohm's law, right? That is, if the resistance increases, obviously the current decreases, inversely proportional. So this is a very important point. This is a very important concept. Keep that point in mind, right? So as the resistance increases, the width of the resonant curve increases, and the bandwidth also increases. Due to that, the selectivity decreases, right? What is the selectivity? First of all, selectivity is the ability of the receiver to select a range of frequencies, right? So that is a selectivity. So it decreases, and obviously the current also decreases. So it is very obvious from this curve, right? That is R3 curve. R3 is greater than R2 and R1. The R3 has very poor selectivity, and R2 has medium selectivity. R1 has the highest selectivity, right? R1 has the highest selectivity. Understand? So this is all about resonant curves in regarding to selectivity, right? So selectivity purely depends on the value of bandwidth, resistance, and how narrower the resonant curves, right? So narrower the resonant curve, better the selectivity. Keep this point in mind. Narrower the resonant curve, better the selectivity. The selectivity will be good. Understand? So for good selectivity, the resonant curve should be as narrower as possible, right? Okay, this point is very important. So to define the sharpness of the curve and selectivity of the circuit, two parameters are very important, right? Commonly asked questions, right? So these two parameters define the sharpness of the curve and selectivity. That's important, right? How sharper the resonant curve is, better the selectivity, right? Okay, that's what important in a resonance circuit. So these two parameters define the sharpness or selectivity of the circuit. That is quality factor Q and bandwidth BW, indicated as BW, right? Now, what is the quality factor? Quality factor formula is Q equal to 2 pi into maximum energy stored divided by energy dissipated, right? 2 pi is the duration of a full cycle, right? So 2 pi into maximum energy stored divided by energy dissipated. So which element stores energy in RLC circuit? Right, reactance stores energy, right? And which dissipates energy? Only element which dissipates energy is resistance, right? So that's a key factor you need to know in remembering this formula, right? That is, in simple you can say that Q equal to XL by R. The only element which stores energy is inductance or capacitance. So XL by R, or we can say that XC by R, right? So what is XL? Omega L by R, and what is XC? 1 by omega C. So 1 by omega C R, right? This omega is called as resonant frequency, right? What is omega? Omega is the resonant frequency. Omega are equal to 1 by root LC, correct? Just substitute the value of omega either in this equation or this equation, right? So this is resonant frequency omega R, correct? So on substituting you will get the value as this, that is Q equal to 1 by omega CR, right? Omega R is 1 by root LC. That is 1 by root LC into CR, correct? That is 1 by root C square by LC, correct? Into R. That is 1 by, both C cancel each other, and the result will be CC cancel each other, right? So the result will be 1 by R into root L by C. On reversing, you'll get the value as 1 by R into root L by C. Okay, so these three formulas are very important. That is Q equal to XL by R or XC by R, or Q equal to, in the both three parameters. In terms of three parameters, we can define the formulas Q equal to 1 by R into root L by C. Very important formula. Okay. And then coming to bandwidth. Bandwidth is the difference between half power frequencies or a difference between minus 3 dB frequencies, right? So consider this resonant curve. This resonant curve has a resonant frequency, right? The resonant frequency is one in which the current is maximum, right? So from the maximum current, subtract 3 dB. 3 dB on both the sides, you will get the value of the lower cutoff frequency and the upper cutoff frequency F1 and F2, right? So the bandwidth is the difference between half power frequencies or minus 3 dB frequencies, that is F2 minus F1, difference between the 3 dB minus 3 dB frequencies, right? That is F2 minus F1 gives the bandwidth. Okay, so what is the formula? Bandwidth equal to F2 minus F1. What is half power frequency? Half power frequency is one in which in that particular frequency the power is half of the maximum power, right? The power is half of the maximum power while current is 1 by root 2 of the maximum current. This is 0.707 of the maximum current. Understand? Okay, so bandwidth is given by F2 minus F1 or omega 2 minus omega 1. Okay. Now we can derive the formula for bandwidth. Okay, the derivation is not important, but you need to know how the formula occurs, right? It's a small derivation only. So first, what is the bandwidth? F2 minus F1, right? So first we can find, or omega 2 minus omega 1. So first we can find the value of omega 1 and omega 2 and just subtract, right? So at F1, that is at the lower cutoff frequency, right? F1 is the lower cutoff frequency, correct? So at F1 or omega 1, what is the value of I1? I1 value will be I max by root 2. At F1, the value of current will be I max by root 2. That's what I'm mentioning here, right? I1 equal to I max by root 2. We can also say that what is I1 square then I max square by 2, correct? So what is I max? I equal to V by R, right? That is V square by R square. I max square equal to V square by R square. That is I1 square equal to V square by 2 R square. Mark it as equation number 2. Okay. Now, also we can say that I1 equal to, so in a series RLC circuit, what is I equal to V by mod Z, right? I equal to V by mod Z, the magnitude value, correct? So V by root of R square plus omega 1 L square. I'm marking it as omega 1, right? At lower cutoff frequency. So omega 1 L minus 1 by omega 1 C, the whole square, correct? So on squaring, you will get the value as like this, correct? So from equation 2 and 4. Both as the left hand side as I1 square, correct? So I1 square. So just equate the right hand side. There is V square by 2R square and V square by some terms, right? So the denominator, just equating the denominator, you get the value as R square equal to, okay, 2R square minus R square equal to the entire right hand side, correct? So from this you can say that omega 1L minus 1 by omega 1C equal to plus R minus R, right? The square rooting, right? So plus R minus R. Correct. So this is at lower cutoff frequency. At lower cutoff frequency omega 1, this value occurs. Correct. At omega 1 or F1. So that is at the lower frequency less than the resonant frequency. Correct. And now at the higher frequency at omega 2, that is greater than omega 2 greater than this omega R or resonant frequency. Correct. The same form of derivation will result in omega 2L. This is just a simple change, right? Omega 2L minus 1 by omega 2C equal to plus or minus R, correct? That is at omega 2. That is at a frequency F2 greater than FR, correct? Okay. Now, just analyze these both two equations. That is at lower frequency less than FR. That is at frequency less than the resonant frequency. What is the behavior of a circuit? The circuit is purely capacitive. Correct. So when the circuit is capacitive, that is 1 by omega 1C will be greater than omega 1L. Correct. So if the second term is greater than the first term, the remainder, the subtraction value results in negative value. Correct. So omega 1L minus 1 by omega 1C obviously result in a negative value. That is minus R is the option. Understand? Now, coming to the second formula, that is omega 2L, this formula, right? That is at a frequency greater than the resonant frequency, the circuit behaves as a inductive, correct? So, when a circuit behaves as an inductor, then the value of omega L will be greater than the 1 by omega C, correct? So, obviously, the result will be positive, right? That is omega 2L minus 1 by omega 2C will be R, only positive value of R. Understand? This is what I am coming to say. From this equation, we can find the value of omega 1 and omega 2. So, from this equation, just cross multiply and you will find the value of omega 1 will be in a quadratic equation form. So, just use the formula. You know the formula minus b plus or minus root of b square minus 4AC divided by 2A. Remember this formula? So just substitute the value in this formula and find the value of omega 1. Correct? It is omega 1 value will be minus R by 2L plus or minus root of this value. You know how to derive, right? Just substitute the value in this formula. Okay, 2 just goes to the numerator, and if it goes to the square root, it will be 2 will be 2 square, that is 4, and here also it will be 4, and just this is common simplification. Okay, got it? So this is the value of omega 1. That is omega 1 will be, the frequency won't be negative. So just I am taking the plus or minus is only plus, right? Omega 1 equal to minus R by 2L plus this value, and omega 2 will be just the opposite sign, that is R by 2L plus the whole value. Okay. Now what is the bandwidth? Bandwidth equal to omega 2 minus omega 1, correct? What is the value of omega 2? This value and omega 1. Just subtracting this, both the terms gets cancelled each other, and R by 2L minus R by 2L, correct? So the result will be R by 2L plus R by 2L, that is 2R by 2L. So the value of bandwidth will be R by L, right? Very important formula. Okay, the bandwidth value will be R by L. Okay. What is the relation between quality factor and bandwidth? Okay, so far we have seen about quality factor and bandwidth. Both these terms are used to define the sharpness of the curve or selectivity of the circuit, right? So what is the relation between quality factor and bandwidth? What is quality factor? Omega L by R or 1 by omega CR, correct? So taking this formula, that is omega L by R. What is R by L? Omega by R by L, right? What is R by L? R by L is the bandwidth of the circuit, correct? So we can say that omega is nothing but a resonant frequency, right? So I am indicating as omega R. So quality factor is termed as the ratio between resonant frequency and the bandwidth of the circuit, right? Q equal to omega R by bandwidth, or we can say that bandwidth equal to omega R by Q. Very, very important formula. Everywhere used in all electronic circuits, subjects and everywhere, right? So bandwidth equal to omega R by Q. Understand? So now we can see a small problem, okay? So in a series circuit of inductance L equal to 15 millihenry and capacitance value and resistance value, what is the impedance at resonant frequency? So in a series RLC circuit, what is the value of impedance? Is it equal to R plus XL minus XC, right? So R is given. We can find XL and XC, right? XL equal to omega L, XC equal to 1 by omega C. But they haven't given any frequency, right? So how to find the value of impedance, right? So given the impedance at resonant frequency. So what is the value of impedance at resonant frequency? That is the key, right? The resonant frequency term is the key. So don't confuse. So what is the impedance at resonant frequency? The question is that, right? So at resonant frequency, what is the value of impedance? The impedance value will be equal to resistance value. So what is the answer? Is it equal to R? That is 80 ohms. The answer is option C. Okay. So at resonant frequency, the impedance will be resistive. So is it equal to R? Okay. So consider this problem. So in the circuit, a maximum current of 0.1 ampere flows through the circuit and the capacitor is at 5 microfarad with a fixed frequency and a voltage of 5 volt. Determine the frequency at which the current circuit resonates. That is our resonant frequency, right? Resonant frequency. The question is asked about resonant frequency, and then bandwidth, and then quality factor, and then the value of R at resonant frequency. Okay, so these are the parameters they have asked, right? Okay, and given the maximum current, that is they have given the value of I max, right? I max value will be 0.1 ampere. I max value will be 0.1 ampere, and the capacitance value is also given, right? Capacitance value is given as 5 microfarad, and this circuit is given in which the inductance value is also given, that is L equal to 0.1 Henry. Okay, so at resonance, what is the condition? At resonance, the current is maximum, correct? So at resonance, the current is maximum. That is I max, correct? What is the formula for I max? I max equal to V by R, right? That is the impedance value will be minimum. That impedance value will be equal to R, correct? So I max equal to V by R, right? Okay, so what is the value of V given the circuit itself? They have mentioned the value of V as 5, right? And we need to find the value of R, correct? So R is unknown. So from this equation, you can easily find the value of R, correct? R equal to 5 by I max. What is I max? 5 by 0.1, correct? That is 50 ohms, right? That is the value of R will be 50 ohms. Correct? And then how to find the value of resonant frequency then? What is the resonant frequency formula? You have found the value of R, correct? R value is found out. And coming to resonant frequency, what is the formula for FR? FR equal to 1 by 2 pi into root LC, correct? So you know the value of L, you know the value of C, just substitute and find the answer, correct? It is easy to find FR. And what is bandwidth? Bandwidth equal to FR by Q, correct? You know FR, but you don't know the value of Q, correct? And now coming to the other formula for Q. How to find the value of Q? Then FR is known from this equation and Q is unknown. So how to find Q? Q equal to, from the circuit parameters, Q value is omega L by R. That is 2 pi F L by R. Correct? You know the value of inductance, and you know the value of this. F is nothing but our resonant frequency, right? If you know the value of FR from this previous step, you know the value of R, everything. Find the value of quality factor Q. Got it? And if you know the quality factor value Q, you can easily find the value of bandwidth FR by Q. Okay, just substitute the value of FR and Q and find the value of bandwidth. Okay, so just substitute the value in all these commonly used formulas and comment in my video also. Comment the solution in my video. Okay, so this is a practice problem for you. Okay. So these are the key points to be remembered in a series resonance. Okay, very, very important key points. Okay. So first, in a series resonance circuit, you know XL equal to XC, right? Inductive reactance will be equal to capacitor reactance. So the impedance will be minimum, that will be equal to R. This is the first important point. The impedance will be minimum. Very, very important point. So if the impedance is minimum, obviously the current will be maximum, that will be equal to V by Z. Z is R. So I max equal to V by R. The current is maximum. This is very important point in a series resonance circuit. In a series resonance circuit, impedance is minimum, current is maximum. Okay. And then what about resonant frequency? F equal to 1 by 2 pi root LC. If in angular frequency, that is omega R equal to 1 by root LC, right? And these are the other important concept is, if the frequency is less than resonant frequency, the circuit will be capacitive. If capacitive, then it has a leading power factor, that is theta equal to 90 degree, correct? And if the frequency is greater than resonant frequency, the circuit is predominantly inductive, that is it has a lagging power factor, that is theta equal to negative 90 degree, correct? And if the frequency will be equal to resonant frequency, the circuit is resistive, and the circuit has unity power factor, theta will be, that is phase angle will be 0 degree, correct? Important point is the resistance, the resonance purely depends on selectivity. That is the very important parameter, selectivity, right? The selectivity depends on the resistance value. The resistance is directly proportional to width. If the resistance is larger, the wider the resonant curve. If the resonant curve is wider, the bandwidth is larger, and if the bandwidth is larger, the selectivity will be lower, and if the resistance is larger, the current will be lower, correct? And we have seen 3 resonant curves, right? So go for a recap, and then that is narrower the bandwidth, greater the selectivity, correct? Very important point, okay? And then what is the quality factor? The quality factor and bandwidth defines the sharpness of the curve, right? So Q equal to omega L by R, or 1 by omega CR, or 1 by R into root L by C, correct? And what is bandwidth? Bandwidth is the difference between the minus 3 dB frequencies, omega 2 minus omega 1, or F2 minus F1. So we have derived this equation. There is omega 2 minus omega 1 is the bandwidth. That is bandwidth equal to R by L, correct? And omega is 2 pi F. So 2 pi F2 minus 2 pi F1 equal to R by L. So 2 pi is common. 2 pi into F2 minus F1 value will be R by 2 pi L. So remember this formula also. Okay, and then this is another important key point, right? That is omega R, the resonant frequency will be equal to square root of the upper cutoff frequency, lower cutoff frequency omega 1 and the upper cutoff frequency omega 2. Omega R equal to root of omega 1 and into omega 2, correct? And the other important point is that the lower cutoff frequency FL equal to, that is F1 equal to the resonant frequency minus half of the bandwidth. And the higher cutoff frequency is F2, right? Equal to FR, resonant frequency plus half the bandwidth, okay? That is FR minus 1 by 2 into what is bandwidth in terms of frequency? R by 2 pi L, correct? On substituting, you'll get the value as FR minus 1 by 2 into R by 2 pi L, R by 4 pi L, okay? Similarly, for the higher cutoff frequency, FR plus R by 4 pi L, okay? So these are the key important points. If you know all these points and concepts very, very clear, if you know these points very clearly, then you can crack any questions in any competitive exams, okay? So kindly revise all these points, okay? In the next video, we can see parallel resonance and compare both, okay? So that's all in today's lecture. So if you like my video, do a like, share this video to your friends and subscribe to my channel Easy Abhay and Tricks and click the bell icon for immediate updates. If you have any doubts also, you can leave a comment in my comment section. And this is Tiki signing off. Thank you.